Hello and welcome to this video on latent growth versus latent change score models. What is the difference? My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis, and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also check out the description for additional resources, including workshops that I teach for QuantFish. In this video, I want to address the question of what is the difference between latent growth curve models and latent change score models. So we want to take a look at those models in a little bit more detail to see what are similarities and what are differences between those models. And at the end, I will also give you my opinion on which type of model is more useful for analyzing longitudinal data. So let's get started. First of all, what do latent growth curve models and latent change score models have in common? Both are suitable for longitudinal studies, meaning repeated measures data in which you assess the same people repeatedly across time with regard to one or more variables. Both latent growth and latent change score models are models of longitudinal confirmatory factor analysis, so they fit right into the general structural equation modeling and factor analysis framework, which means they both can be estimated within software that is appropriate for structural equation modeling and confirmatory factor analysis, such as, for example, Mplus, Latent, Amos, Lisrel, EQS, MX. All these kinds of programs can be used for estimating these types of models. And another thing that latent growth and latent change models have in common is that both allow us to model change as a latent variable, meaning we can look at inter-individual differences in change across time at the level of variables that are corrected for measurement error. So we can separate measurement error from true change with both these types of models, and that's one of the primary advantages of both models, is that they allow us to look at true changes over time, meaning variability across time that is not due to random measurement error, which could distort our analysis of changes across time. So we can look at changes in individuals' true scores across time that is not contaminated by measurement error. So those are some of the broad similarities between these two types of models. Now let's dive deeper into the structure of latent growth and latent change score models to see how they differ. And I'm going to start with latent growth curve models. Specifically, I'm going to show you a linear growth curve model here, which is one that is very frequently estimated when people apply growth curve models. And then later on, I will point out that there are also other versions of a growth curve model that do not necessarily require a linear trajectory across time. So what does this look like? Here we're going to consider single indicator models where we have a single repeatedly observed variable. For example, let's say we have intelligence scores or school achievement scores on 4 different time points. So this would be for example, could be the SAT scores at time 1, time 2, time 3, and time 4, a continuous variable that is measured on 4 occasions of measurement for the same individuals. And now in the growth curve model, we have an intercept factor on which all 4 time points load with fixed loadings. All the loadings are fixed at 1, which makes this factor the intercept factor. And then in a linear growth curve model, we also have one slope factor, or sometimes we call this a shape factor or a linear change factor, we could say, where the loadings are also fixed. However, they're not all fixed to 1. Instead, the first loading of the first time point is fixed to 0, which you can't see here directly because there's no arrow indicated between the slope factor and y1, which means that loading is 0, which makes sense because at time 1 no change has taken place yet. So there's the first loading appears for y2, and that loading is fixed to 1. The next loading is fixed to 2 and then 3. And if we had more time points, then it would keep going like this, assuming that the time points here are equally spaced. So if not, then you would have to change the loadings according to the time metric in order to still make that slope factor a linear slope factor. Furthermore, intercept and slope factor are allowed to correlate, so there can be a relationship between the initial state and change over time. And we have measurement error variables epsilon, which shows us that this model allows us to separate true inter-individual differences from random measurement error, and that's one of the primary reasons why we use latent variable models to assess changes across time, so that we can have a cleaner separation or a cleaner assessment of changes across time, where we can be sure that change is really true change and not change due to measurement error. We can summarize this model with a relatively simple measurement equation that here says yt, so the score or the variable at time t is a function of an intercept plus a loading that is t minus 1 times the slope factor plus measurement error. So t here is time, and so t minus 1 gives you the slope factor loadings, as you can see here. So this is time point 2, and so 2 minus 1 is 1, and then 3 minus 1 is 2, and so on for linear growth. So that's a pretty straightforward model that consists of this one measurement equation. There's an intercept factor component for all variables, and there's a slope factor component for all variables that are measured past time 1. Now, how do we interpret those latent factors? The intercept factor can be interpreted as the true score at time 1. So that's a variable that represents true inter-individual differences, for example, in school achievement or intelligence at time 1. The slope factor gives us the rate of true linear change that can differ between individuals. So some individuals may change a great deal, other individuals may change not at all or very little. There can be positive changes, negative changes, and so the score on the slope factor indicates a person's rate of change, rate of true change across time, and it's assumed that it's linear for everybody in this model because the loadings are fixed in this way, which defines the slope factor to be a linear change factor. Now, this need not be the case. There can also be latent growth curve models with nonlinear trajectories. So you could, for example, add a quadratic growth factor to the model so that the trajectories don't have to be linear but could be curvilinear. Also, there are models available that have free loadings here. So rather than fixing all the loadings for linear change, we might estimate the second loading here for time point 3 and the loading for time point 4 to allow for an unspecified growth function where the change across time does not have to be linear, but instead is estimated from the data. So where we do not even impose a certain growth component or form of change across time, but where the shape of change is estimated from the data. And I have a separate video here on this channel that is called a free growth curve model video, where I discuss a model with free loadings as well. And also in my book, Structural Equation Modeling, Longitudinal Structural Equation Modeling with Mplus, I discuss other growth curve models and also change score models. So in the description, you find the link to that book as well. So this is what the linear growth curve model looks like. Now let's take a look at the latent change score model. And so in the latent change score model, again, we have longitudinal data or repeated measures data, and I'm assuming that it's the same design here with 4 measurement occasions and a single indicator or a single measured variable that was repeatedly assessed across time. So this is exactly the same thing as in the latent growth curve model. But now we have a factor at time 1 again, so F1, but we also have factors at each of the other time points in this model. So F2 is the true score at time 2, F3 is the true score at time 3, and F4 is the true score variable at time 4. And we have latent change score factors and more than one. So in this model, we have a change score factor F2 minus F1 that represents true changes in the factor scores between time 2 and time 1. Notice that the factor loadings here, or these paths in the structural model, are fixed at 1 such that this factor can be interpreted as a change score factor, because then we have a structural equation, as we will see later, that says F2 is 1 times the previous factor plus 1 times the change. And there's no residual here, so there's no residual variance or variable for F2, and that's important. So F2 is completely determined by F1 plus change, and so fixing those loadings here is required, or those paths, in order to make this the change score factor. Furthermore, there is a path between F1 and the change score factor, a regression path, or latent path coefficient beta 1, 2, so that changes can depend on the previous state. So whether somebody changed a lot or not so much might depend on what score they had at time 1. And that parallels what we do in the growth curve model, where we allow the intercept factor and the slope factor to be correlated. Okay? And then there is actually a residual here, because we may not be able to predict the entire variance in the change score factor from the previous state. And so there's a residual zeta 2 here that reflects residual variance in the change score that cannot be predicted by F1. And so the same structure here we have also for F3 and for F4. So the same principle of having a change score variable that represents change between the adjacent measurement occasions, and there's a residual here for this regression of the change score factor on the previous state. So you can see one difference here between this model and the latent growth curve model is that there are multiple slope factors, so to say, or multiple change factors, one for each pair of time points, so that we can model changes for each of these intervals. So it makes it a little bit more flexible, and change doesn't have to be linear. So there could be more change, for example, between time 1 and time 2 than there may be between time 2 and time 3, and that's allowed in this model because the change score factors are estimated separately for these different intervals, and so there's no need for change here to be necessarily linear. What else do we have here in this model? Again, we have measurement error variables, so that parallels what we have in the growth curve model that reflect unreliability of our measurements. Now, this model here, how can the variables be interpreted? F1 is, in terms of its interpretation, parallels what we have with the intercept factor in the growth curve model. So the true score at time 1 here, that's our intercept, so to say. So that has exactly the same interpretation as the intercept factor in the latent growth curve model. The change score factors have a similar interpretation to the slope factor. They again represent true inter-individual differences in change across time. So how much people differ in terms of how much they changed. However, there's now multiple such change factors, so that we can look at changes between all these different pairs of measurement occasions. So that reflects true changes between adjacent time points in a similar way as the slope factor represents true inter-individual differences in linear or other change in the growth curve model. And we have measurement error, as I already mentioned. Now, this model here consists of more than one equation, because here we have a measurement model for which you can see the equation here. So yt is equal to ft plus epsilon t. It's a simple true score equation as in classical test theory for each time point. But then there's also a structural model here, where we have relationships between the latent variables, the factors. And so the first equation here specifies that a factor at time t is a function of the previous factor, ft minus 1, plus change ft minus ft minus 1. And that's reflected in these paths here that are fixed to 1. So that's this model where it says f2 is equal to f1 plus 1 times f2 minus f1. So there are these implicit coefficients of 1 here before ft minus 1 and before the change score factor, which are not shown here. And that's why these are fixed to 1. And so that's the case for each of these, for f2, f3, and f4. They're always a function of the previous factor plus change. And now there's another structural equation for these betas here, because the change score factors, they are regressed on the previous state or the previous factor. And so therefore there's another equation that says the change score ft minus 1 is equal to an intercept beta 0t plus a slope coefficient or path coefficient beta 1t, which you can see here in the picture, times the previous factor ft minus 1 plus a residual zeta t, which you can see here at the top. And so when we combine all those equations where we can insert what we have here for ft into the measurement equation, and we can insert what we have here for ft minus 1 into this equation here, then if we combine those together, then we have a measurement equation that summarizes the entire model in the same way as we saw that for the growth curve model, but it's more complex. So this says that yt is equal to the previous time point factor plus change. So that's this whole term here with the betas and the zeta. This is the change. And then plus the measurement error variable. So it's kind of similar to what we have in the growth curve model, where a variable is a function of an intercept plus slope plus error. But here the variable is a function of the previous factor plus change plus error. Okay, so it's a little bit more complex than the growth curve model. Let me summarize what we have seen here for latent growth and latent change score models. And I'm going to start with the latent growth curve model again. In summary, in the growth curve model, we have an intercept factor and then one or more slope factors that often represent a specific functional form of change across time, for example, linear change or quadratic change, but that need not be the case. We can also estimate the growth curve freely from the data, or we can have a piecewise growth model provided we have enough time points where the different pieces can be different. This model allows us to separate true linear or nonlinear change from measurement error. We can identify linear change already with 3 time points. So that's important because that's a little different for at least the single indicator latent change score model. So we need only 3 time points if our interest is just in linear change. For quadratic change, you would need 4 or more. And in this model, we don't have to place any equality constraints for identification on the error variances. The error variances can be freely estimated, which is an advantage in cases where the reliabilities of the variables change across time. So when you have measurement error variance components that are not equal across time, which we often see in longitudinal studies, that initial measurement occasions have more error variance because individuals have to get used to the procedure, and so then later on the error variance is smaller, and so then it's an advantage when you don't have to put a restriction or equality constraint on those error variances, which is not needed in the growth curve model. You can also relate the growth factors to external variables. So both the intercept and slope could be used as outcome variables that are predicted by other variables, or they could be used as predictor variables, or they could be correlated with other variables. So that's also possible. And for growth curve models, there are both single and multiple indicator versions available. Here I only showed you single indicator models, or a single indicator model, but I have videos on this channel here where I also present second order growth curve models, which are useful. They're more flexible because they use more than one measured variable at each time point. And I also describe these models in detail in my book, Longitudinal Structural Equation Modeling with Mplus. Now let me summarize latent change score models. In latent change score models, we saw that there's also an intercept factor or an initial status factor for time 1 that represents true inter-individual differences at at the first measurement occasion. And in contrast to the usual growth curve model, in change score models we have multiple change factors. So in growth curve models we could have multiple slope factors, but oftentimes we may have only a linear factor that represents the entire linear trajectory across time. In contrast, in the latent change score model, there's a separate latent change factor for each pair of time points, so that we can look at changes, for example, between time 2 and time 1, time 3 and time 2, time 4 and time 3, and so on. Again, it allows us to separate true changes from measurement error in a similar way as this is the case with growth curve models. In terms of identification for a single indicator latent change score model, we need at least 4 time points for this model to be identifiable. This is different when you have multiple indicators. So when you have more than one test score variable that is repeatedly measured, then you can apply latent change score models already with just 2 time points. And that's a huge advantage of latent change score models over latent growth curve models, because when you have multiple indicator data, or you have multiple items or multiple scales, then you can already apply this model to a design with just 2 time points. And I have separate videos on this channel where I discuss multiple indicator latent change score models. So check those out. You can see then how this works when you have multiple indicators. And that's actually the way to go, in my opinion. So it's always better to have multiple indicators because it makes the models a lot more flexible. Now, one other disadvantage when you have single indicator data is that you have to place constraints on either the measurement error variables epsilon in this model or on the latent zeta variances for the structural model. And so those equality constraints that you have to place for identification in the latent change score model may or may not be plausible. So I tend to think that assuming that all the error variances are equal across time is rather unrealistic, because in longitudinal data that is typically not the case. So then you might end up deciding to set the latent zeta variances equal across time, but that's also not necessarily plausible. That is different again when you have multiple indicator data, then no such equality restrictions are required in a latent change score model. So that's something to consider, to use multiple indicators, which makes these models a lot more flexible. Like in latent growth curve models, in latent change models, you can relate the factors to external variables to predict change across time, for example. So for example, you might be interested in explaining why did some children change more with regard to their SAT scores than others. So what determines that? Is it, for example, the type of schooling or other variables? So those can be added to a model in the same way as they could be added to a growth curve model. And then finally, I already mentioned that you can apply these types of models to both single and multiple indicator data, and my recommendation would be to use multiple indicator data whenever possible, because then the models become more flexible and also more easily identified. And so now finally, I promised you that I would give you my opinion on which type of model I prefer, latent growth or latent change score model. And I personally tend to think that latent change score models are often more flexible, because it's often difficult with latent growth curve models to determine a form of change that applies to everybody. So it's a very restrictive assumption, for example, to assume that change is linear for everybody. So everybody has a straight line trajectory of their true scores. That's not necessarily restrictive. Also, everybody's trajectory is quadratic, and quadratic is also not necessarily always so plausible, because why should it be U-shaped or inverted U-shaped? So that can be difficult to fit. Oftentimes, latent growth curve models don't fit so well, and then people end up trying out all kinds of different trajectories and or a growth curve model with a free growth trajectory, and that can be a problem to find a fitting model there. Also, in a growth curve model, you have only one slope factor typically, and so that slope factor represents the entire trajectory, whereas in a latent change score model, you have a slope factor or change factor for each pair of time points, and that can make the analysis more flexible. And in my experience, oftentimes latent change score models are easier to fit. They fit the data better than growth curve models, especially when you have growth curve models that have a very restricted growth curve, such as, for example, a linear growth curve. I hope you found this video useful. To learn more about growth curve models and latent change score models, please consider subscribing to this channel. Don't forget to check out the description for additional resources, including workshops on longitudinal models and growth models that I offer for QuantFish, as well as my book on longitudinal structural equation modeling with Mplus, and I'll see you next time.